over genetics did. I had to steal and sneak my way into the building. These guys were great.
Excellent. Well, I think I'll start this stream. I'm going to record it too, just in case.
Okay.
$11 people waiting now.
I just wait 2 or 3 more minutes. That's
Okay. Yeah, for those of you watching on the stream, we're waiting on some more people to show up. So, welcome to Went Commons Room 410, which is not the normal Weather Watch space, but it's a beautiful room. And John Martin will be your master of ceremonies today, Professor John Martin, and he'll get going in a few minutes here. So, welcome on the stream, and if you have any questions or comments, please feel free to post them in the chat. I'll just put one there now and welcome everybody.
okay, I think we're going to get going.
Okay.
Welcome everybody to our weekly weather discussion. Those of you in 751, thank you for finding the room. Most of you did. And I have a lone participant from 452, Elizabeth. Thanks for coming. I think you find this useful because those of you in 751 will have to mount the effort to run one of these 1-hour discussions sometime late in the term. And you can do it with a partner, so it won't be just you by yourself. But I think you'll get an idea from the several that occur before your time of what will be involved in the effort. And Chelsea already asked me, just to let you all know, Chelsea asked me if there is a rote sort of thing that has to be included in every single discussion. And I think those of you who have been attending this for the last couple of years would realize the answer to that is no, but it's an excellent question. It can't be, I guess, probably far off. We probably don't want to know about the Uranian spring probably for a whole hour in the weather discussion. We want to get a little bit of the current weather and something on the forecast. But your example of sub-seasonal forecasting and issues related to that is absolutely valid. So just about anything goes. And so I think you'll see how this works throughout the rest of the term. Can you hear me okay with this? I don't usually use a microphone, but it's going to help because I was out of breath yesterday a lot of times. So I'm going to try this today. So we'll start, I often start by looking at the current weather and some representations of aspects of it. And I start with the satellite picture. So here's the visible satellite movie for the last, I think, 6 or so hours. And over much of, a large fraction anyway, of the Western Hemisphere. Here you can see northern South America. Beautiful cumulus clouds developing over the land as the sun comes up, and they're kind of widely spaced, so it's kind of a nice fair weather cumulus day over much of the countries of the northern part of South America. The same is true over a large fraction of the Atlantic, you can see. And then over our own country, we have a weather system up in central northern Ontario that's still looking fairly impressive, maybe on the western side of it over the eastern portions of James Bay and the Hudson Bay. It might even be snowing or at least raining with temperatures in the low 40s. We'll see in just a minute. Beautiful day for us. We've had a succession of them, as you know. I think Tuesday was probably about the nicest day that we've had here in, I don't know, at least a year. It just was an absolutely beautiful day. Yesterday wasn't too bad. Started out windy. We'll talk about that storm that's up in Ontario in some detail. Much of this discussion will be dedicated to that. And so you'll have a little bit of a glimpse of what's going on with that. Not so heavily populated map. You see some heavy rain in some of the stations here in central part of the state. Lighter rain to the north. But in the central part of the state, dew points prevailing in the 70s and temperatures about the same, so you're just about saturated. and it's precipitating in some places heavily. Okay, and then there was not much on the Pacific Northwest weather-wise. You'll see they don't even start school in Seattle till late September on purpose, because that is the university, because the weather is so nice. Look at it, 69 over 56 today, beautiful day. Light easterly, northeasterly wind means it's going to stay dry, it's going to stay clear. So that's very nice for them. And the best month of the summer is September, so they don't even bother with using it for school. Okay, let's go to our upper level charts. And I'll show you the 500 millibar map from this morning at 7 a.m. And there's a broad scale upper trough dominating the eastern part of North America. This is a very unusual looking weather map for early September. This looks like something more characteristic of late November, early December, maybe even later than that into the winter. Because as the winter progresses, one of the climatological features is the so-called Hudson Bay Low, and that gets itself strongly situated here. There's upstream variations, ridges and troughs come and go in the Pacific Northwest. Sometimes for long periods of time, it's one or the other. A big ridge down over the southwestern United States is not uncommon in September, but I think the establishment of what looks like the establishment of the Hudson Bay Low this early is somewhat unusual. And it comes with cold temperatures. We have temperatures, in the minus 15 range at 500 millibars in northern Michigan. It's colder than that in the upper peninsula, and widespread minus 20s and colder over southern central Canada. So that's very interesting. A pretty intense horizontal temperature contrast. The red lines on this map are isotherms, lines of constant temperature, at 500 millibars, which is about 3 miles above the ground. And to see a gradient or a contrast zone that strong this early in the season is somewhat unusual. And it's related to the weather system that came through just to our north yesterday. And I'll tell you some more about that as we continue with the discussion. Okay? So pretty nice, almost winter-looking pattern, at least over the eastern two-thirds of the United States, prevails today and certainly prevailed yesterday at 500 millibars. At 300, which is a little bit higher, come on, help me out here. There we go. At 300, which is at about 6 miles, no, that's not what I wanted to do. There it is. What we contour on this map, along with the isotherms, which are in red, is values of constant wind speed known as isotachs. So you can see in the colored regions where the wind speed is large. Any place where it's white, it's over 130 knots and so on, and the purple is 110 to 130. So, and here's Wisconsin. So we're right at 7 a.m. this morning, we were just about at the trough axis for this large-scale wave with some upstream jet structure and some downstream jet-like picture. Unfortunately, only southern Canada, right near the border, has an array of radar stations, and nothing from the central part of the country to the north has any radar. So we don't know anything about the precipitation distribution in northern Quebec with this storm. But I guess that's what it is. That's where it's focused. Okay. What was I going to show you next? Oh, I guess before I go into a more detailed diagnosis of the recent storm, I want to show you what the current forecast model shows us. The GFS shows us about the structure of this event. And I guess I'll start by going to, I should have got the old one. Anyway, you'll see some other evidence of older structures. This map is the 500 millibar map, so this is about 3 miles above the ground, I think I mentioned to you before, and what I showed you before was an analysis of the real data with isotherms on it. Now, we're looking at a model analysis, which takes that data, runs it through its pre-forecast scheme as a way to think about it, and then takes all of that information, including information from prior forecasts, and creates what's known as an analysis. And I'm showing you in the shading here the vorticity, which is a measure of the spin of the air parcels in the flow. And this turns out, for reasons that you'll learn about a little bit later in your studies, this turns out to be a pretty important variable. And what it does is it links the divergence to vertical motions really nicely, the vorticity does, without forcing us to do the integration of the continuity equation. It's a really great device for helping to understand the development of weather systems, how this vorticity is moved around differentially at different levels and so on, has a lot to do with how divergences are forced and how the air is forced to move up and down in the vertical. And it's the up and down motions of the air that either gives us a beautiful day like today where the air is gently sinking, or gives us a stormy day, which is the kind I like better, when the air is maybe gently or vigorously rising and producing clouds and mayhem. And that's what makes it interesting. So you're looking at the late stages of a pretty nice development here. And I don't have pictures of the vorticity maps. Well, I do, because I have this 5D. I'll show you what it looked like beginning yesterday, actually Wednesday, what's today, Friday? Actually Wednesday evening, 0Z on Thursday. What did this structure look like then? It doesn't look quite as spent, I guess is the way I look at it. It's only a central maximum here in the far southeast shore of Hudson Bay. That's not by coincidence that it sits about where the cyclone center is at this late stage in the life cycle. That tends to be the case in almost all such mid-latitude developments. But we'll take a look at where this structure, how this structure evolved over a short period of time at this level in just a second. In fact, I think I'm going to go and do that by going back to these maps right here, and I'll get a loop at 500 millibars. And we're not going to spend time on every piece of the loop. I just want to show you the maps that count in this evolution. And I'm trying to read through there with my bad prescription here. Okay, so let's start with Tuesday night, 0Z on the 2nd of September. It's this little wave. You see this little bit of a dip in the geopotential height lines, which look black on this map? It's right off the coast of British Columbia. It's that little dip that turns into a substantial wave. Looks more like a carved out trough as we move forward in time. So these are every 12 hours. So there's 12 hours later. This would have been Tuesday morning for us. And right over central British Columbia, pretty nice little trough has built itself out of what seemed to be almost nothing earlier. And so you've got a nice looking structure there. Importantly, for reasons that come out later in your dynamics courses, this structure will develop a little bit more if it's characterized by cold advection back here and some warm advection in this region. And in fact it is, especially the cold advection over southern British Columbia. That tends to make the trough more intense. And the more troughy the weather is, the more the flow has to curve, change direction. And when it changes direction, it accelerates. And when it accelerates, there's something out of balance, because that's what acceleration means. You've got a whole bunch of forces acting on something. If they don't balance, then there'll be a net force pulling you in a direction, right? And that's the acceleration. So here's the next time, which was 0Z on the 3rd, which is where I'll begin my Viz 5D in just a minute. Look at this trough now over southern Saskatchewan and northeastern Montana. That's really sharp. The change in direction of the flow is quite dramatic. And the temperature contrast has gotten really sharp. These lines are always drawn every 5 degrees, but looking at the prior map and then this one, let's see, I can't remember which button it is, can I? Yeah, okay. Every one of these red lines is separated by 5 degrees Celsius. So at the prior time, in the vicinity of the trough that's developing, you have about that much horizontal distance on the map that corresponds to about a 10-degree contrast. At the next time, the 10-degree contrast, the distance between successive lines, is shrunk almost in half. And that means this upper temperature contrast is getting stronger and stronger, and there's reasons why that's connected to the intensification of the upper trough. No matter what class you're taking, 751, 452, or 141, you'll learn more about why that's the case throughout the semester. Perhaps more so in the senior and graduate class. But that's a really interesting development. When you see that happen, you know that to the east of this development, there's going to be a tendency for the sea level pressure to fall in the lower part of the troposphere. And then here we are at 12Z yesterday, when we had pretty strong winds, 7 a.m., and we have a really nice upper trough. Look at how sharp that curvature is. At International Falls, the flow is from the northwest, and even though we don't have a station right on the north shore of Lake Superior, we have one downstream at James Bay. That's from the southwest. That's about a 90-degree wind shift. And this wind is probably very much like a wind we would have observed right here. So that's a really strong wind shift, which means you've got to pull hard on that wind to change its direction. Lots of acceleration, lots of imbalance. And the imbalance leads to divergences in vertical motions. Okay? Notice the horizontal temperature contrast remains quite intense on the western side, or to the west, I should say, of that upper trough. So it's a really nice development, especially for this early in the year. It's canonical development, actually, one that you see over and over and over, and so it's well worth the time thinking about it. And then that's last night, where the initial wave, the initial trough has moved to the border of Ontario and Quebec. It's maintained a really strong temperature contrast that was over us yesterday during a beautiful afternoon. You don't see it, but it's there. And then the cyclone was roaring into northwestern Quebec. And then finally, this morning, we already saw that kind of broad upper trough. And now you can see right in here is where the original wave is. And it doesn't look quite the same as it did before. In fact, the thing that's more obvious is the downstream ridge. But the combination of this ridginess and this now diminished troughiness is enough to maintain the accelerations that force the air to rise in that location. Okay. So let me show you some of that evolution from a slightly different perspective. This is a program that takes the output from the GFS, the Global Forecast System model from NCEP, and allows us to look in 3 dimensions. We might not do much of that today, but we're going to do that for sure at other times during the term. This is the vorticity, all by itself in blue, over the continental US and southern Canada at, I think, about 400 millibars, just a little bit higher than the level we were just looking at. And this is initialized at 0Z on the 3rd of September, so yesterday. So this is about the time when we were getting our pretty decent storm starting itself to get organized over northern Minnesota and Lake Superior. So one gets the impression with these lines, don't worry so much now about the values, but you can see that there's a concentration of this quantity or this substance called vorticity that's right in the vicinity of Wisconsin. So here's Dane County right here. Okay, I guess I'm trying to find the state boundary. Yeah, there's Dane County's right there. And so this is a pretty impressive, very large scale upper wave that's right over us yesterday at, is it 12Z? Yeah, that's yesterday morning, okay, Thursday morning. And then if I march forward, let's see if I can do that. Oh, I know why it's not doing it. Now it will. These are every 3 hours, and you can see that front edge of that thing rolling up and going into not British Columbia, Quebec and James Bay. So it looks like a giant fist, you know, going across northern North America, northeastern North America. And that's really how they look in a variety of different perspectives. Some of those perspectives, you can see, this is a satellite movie that Pete constructed for us for yesterday's weather, and I'm just going to point out as I run it again, it's right on the border of the US and Canada. Look at that beautiful comma-shaped cyclone. Okay, keep your eye on that when I move it a couple more times. That's the storm we're talking about. Absolutely textbook structure, and we were always on the north side of the cold front as this thing developed to our north and east. Or just about always. Beginning right about that time, we had not much to worry about from weather with this storm. Clouds moved out in the morning. So that's a very pretty looking storm, and you don't get them to look better than that. Here's a really interesting thing. When you look at it, the same storm from the so-called water vapor channel. So there's a whole bunch of infrared channels. Some of them are particularly sensitive to water vapor in the upper troposphere. Look at how that same storm looks. There's a big dark spot that kind of is right in the middle of that circulation. The higher white is just high clouds. They're radiating, well, it's actually high values of water vapor, but they're radiating at a pretty cold temperature. The dark spot indicates that there's no water vapor at all in there. So this is very dry air in the upper troposphere, and that dry air, the reason it's dry, has something to do with the way in which the storm develops. Oh, I've just violated all university rules. This is a challenge. You know, my kids were in shows in high school. They use these things all the time. I don't even know how to put it on my head. So I hope it's working. Okay, so beautiful structure to this storm from a variety of different ways of looking at it. So really, one could go on and on and on about what we're seeing here. And I think as the semester goes on and you know more about how these weather systems work, it'll be more interesting to pursue some of those lines and see what we learn by doing so. Okay? Okay, so Pete, thanks for putting those together for me. I didn't use them all, but the ones I used were very, very helpful. So what I think I want to do next is, don't need Viz 5D anymore. I'll leave it because I don't know if anybody else wants to ask any questions about it. I do want to show you something though, and that is a PowerPoint presentation that I decided to make this because I don't know if I was going to have an easy time running GEMPAC live in a new setting. So I decided I was just going to make all these images and then show them and describe what we're looking at. So this is sea level pressure from, I never get the day right, Thursday at 0Z. Okay, so we have a little bit of a weak cyclone in North Dakota at sea level. Wednesday evening, first getting developed. The pressure is 996 millibars at the center of that. This is from a forecast run at 0Z on Wednesday night. And then, for some reason, I only went to the next 6 hours in this first iteration, but this 6 hours later, this thing is a little bit deeper. The 996 contour is expanded, which means the pressure is lower in the middle, right about at International Falls. Importantly, the pressure gradient's intensifying around the storm, and so that's where the hot, strong winds came from for us Wednesday night into Thursday morning. Then I'm going to go every 3 hours. Then we go down from 996 to 992. Then I think it gets down to about 988 and so on. You can watch it just march across southern Ontario, central Ontario maybe. And then finally we get to the 24 hours, 27, 30 hours. The lowest pressure in this forecast run was 978 millibars, and that's about what was actually recorded. So a 978 low in central Ontario in early September is not common. So it's a pretty decent storm. And so I want to show you some of the vertical motion diagnostics associated with this storm that I calculate every day. So it's just pulled right off of what I do every day just for the fun of it. Okay, so that's where the storm went. Nice track all to our north. So for a period of time while it was developing rapidly, and it was, we had that strong gusty wind in Thursday morning. It was related to the development of this storm. Here is the 0Z Thursday morning forecast of 500 millibar vertical motions. It's not actually a forecast, it's done from an analysis. And it's the quasi-geostrophic approximation to the vertical motions at 500 millibars, because they tend to be smoother and you can kind of see where they come from. Where it's yellow, the air is rising at a certain rate. Where it's green, it's sinking. And here's where the cyclone was beginning to develop in southern North Dakota. So it pays some allegiance to where the air is rising. That makes sense. As the air rises and leaves the air column, what's left in the air column simply weighs less than it used to, because there isn't as much air there anymore and the pressure drops. So that's how you get a cyclone. So I woke up on Thursday with the wind blowing. I thought, I do this a lot, I honestly do, that, man, there's a lot of stuff going on in 3D outside today. There's upper divergence, there's low-level convergence, there's air that's rising up and leaving the column, and that's why the pressure's falling. And when the pressure falls, it intensifies the pressure gradient around the cyclone, and the circulation gets stronger, and all these things fall out from that. So trying to understand those things, basic as they are, is what I've been doing for the last 30 or so years. It's really fun. Now what you can do with this total vertical motion field is you can split it up into two pieces that add to the total, but that describe totally different things. One piece is the so-called shear-wise part of the vertical motion that has to do with the very large wave scale. And then the other part is the transverse, which has to do with the fronts. And the fronts are not well resolved in this approximation, but if I split this total into its shear-wise piece, that looks like almost the whole thing, right? And that's what you get from the frontal part. So the frontal part is weak early in the storm. It doesn't have much to do, and it certainly is not close to the position of the low pressure center. 6 hours later, look at how much more intense the updraft is, and it's right sitting on top of the cyclone. So the air is diagnosed to be rising rapidly in that column, and that air is just being exported somewhere else, and the pressure keeps falling at the surface as a consequence. So they have this perfect relationship. And then if I split it again into the shear-wise, looks again very much like the total. And then there's the frontal part. Well, just a little bit of yellow near the cyclone center from the frontal dynamics, but not the main part of it. Then the next time is 12 hours in the forecast. Again, really nice correspondence between the position of the low at that time and the intense updraft in yellow. The core of the updraft is right underneath the cyclone, or right above it, I should say. And if I split this into its shear-wise piece, boy, that updraft looks like the whole thing just about. And here's the frontal part. A little bit more frontal contribution to the development when I get this late in the life cycle. This is about when it was windy here in town. And you can see we were experiencing our frontal passage about that time. Here's the updraft associated with the front, as best as it can be approximated in this quasi-geostrophic framework. And then here's the ascent associated with the warm frontal part of the cyclone. And some of that overlaps with the updraft over the cyclone center. And then here's 18 hours, again, pretty nice relationship between the position of the low and the intense updraft. When I split the two pieces up, now it starts to look like, well, it's not the whole story, the shear-wise part. In fact, look at how much contribution the frontal ascent makes over the position of the low pressure center. It keeps getting stronger. And then here's 24 hours into the forecast. Wow, big difference. And so you can see that as the storm moves into the late part of its life cycle, the frontal part of the vertical motion starts to overlap with the position of the low, and it helps to contribute to the development. That's not true early on. And so this is the last time where you see the exact same thing. Although by this time the storm itself is getting weaker, the total vertical motion shown here at this hour is not as strong as it was at prior times. And then the split is about 2/3 for the shear-wise and 1/3 for the transverse. So that's about how this storm went. It didn't have a strong upper-level front. We'll see some of them as the term goes on. It had a pretty strong upper-level vortex structure, and that was reflected in some of these vertical motion distributions, as it turns out.
John,
Yeah.
does that mean, if that's the case, does that mean that early on it's not so much driven by potential energy, by overturning, that I would think a front suggests that it's called air sinking, warm air riding direct.
Yeah, yeah.
But early on it's more of a dynamic phenomenon, perhaps barotropic almost.
Yeah, yeah. How about this? I'll suggest that, yeah, the larger piece of the ascent comes from the shear-wise vertical motion, which is what Dan Kaiser originally called the wave scale vertical motion.
Right.
And that's exactly what you're talking about. It's the part that arises from changes in the speed or direction of the wind, not so much changes in the horizontal temperature contrast. Exactly right.
So when you get these big bomb cyclones in the fall,
Yeah.
I won't call them bomb, but just cyclone type
Yeah.
cyclones. Cyclone was a big cyclone that occurred over upper Midwest in the fall last year. And it was unusual because it didn't have very much thermal contrast. There wasn't a lot of cold air and warm air contrasting.
Yeah.
And yet it was one of the strongest cyclones ever to hit the Midwest. That must have been totally shear-driven baroclinic coming from the upper levels.
Yeah, I suspect that's right. And maybe a lot of change in direction of this, a trough ridge couplet that was fairly strong.
Mm-hmm.
Some of that gets built, as you know, when the storm itself develops. The cloud head forces the ridge a little bit. We'll talk about that as the last piece of the discussion today. But yeah, I think that's right. I think there are times when, and they're probably not very common, but they happen and they're notable when they do, when the baroclinic tightening that's associated with cyclogenesis in many instances is not so strong. And the consequence is whatever you get for your cyclone development comes from the wave scale dynamics without much assistance. This storm looks like it had about the kind of assistance that I see when I look at this partition on a day-to-day basis in the cold season. It's more fun to look at it in the cold season. I see this is about the way it works. The storm gets to about the peak of its mature stage, and then the frontal dynamics do seem to play a role in subsequent development that leads it to the occluded stage, but not in every case, as you point out.
So the conventional wisdom, we call these frontal cyclones, but it's probably not a very good term in the sense that they're a hybrid cyclone. They're frontal, and yet they have this other wave dynamics. And so I think sometimes the cyclone is more wave dynamics and less frontal, and other times it's more frontal and less wave dynamics.
I think that's right. The original model, about 100 years old now, the Norwegian model suggested you don't get cyclones unless you have a pre-existing front. And Phillips came along with his experiments in the 50s and said, no, the fronts form at the same time as the cyclone. And then now I think I'm at the point where I say that I think that the cyclogenesis leads the frontogenesis a little bit. It begins to produce the deformation fields and so on that can tighten the baroclinic zone. And then the baroclinic zones can, in many instances, aid in subsequent development. But as you point out, not always. And so, yeah, you're right. I think every storm is going to have a little bit different mix of those two potentially contributing factors.
I think it can go over the top completely, in the sense that this time of year, a lot of times the upper level dynamics are powered by the tropical phenomenon, like tropical cyclones, and their outflow produces a strong upper level dynamic that can initiate extratropical storms.
Yeah.
And as they're initiated, they will create a front. So it can go in the other direction, that if there is no front, if there's enough upper level dynamics, it will create the front to go with it.
Yeah.
You know what I'm talking about?
I do, and I think that we even have what you might call more canonical examples of that, I think, are the process by which an upper front develops. I thought for sure this storm would have a really strong upper front. It has a decent upper baroclinic zone, but there's no particularly strong PV pendant that's hanging down. There's no evidence of an overturning circulation aloft. And that can be completely forced by mid-latitude processes, but as you point out in a lot of our discussions in some of your papers, it's clear that the tropics are nudging things in that direction quite a bit.
Yeah.
And in fact, what's going on in the Pacific right now is an example of that. So I want to finish with showing that as an example, because I think you're going to talk about this probably a lot in your class, and this is perfect to have it on the first day, a nice example of that. But that's a really good point. It's an excellent point. And you know, Greg and I have discussions like this every Friday at our weather discussion, and usually Michael Morgan, he's on sabbatical, he's usually here to throw in his 2 cents, and then anybody else who's in the room throws in their 2 cents. This is why this is an informal discussion, but we often end up talking about it. Well, in normal times, we'll be arguing all Friday afternoon about something that we were talking about in the weather discussion, and that plants the seeds for research projects that are funded at the highest levels. So this is a really excellent informal seminar that we have every week, and so I'm so glad you can all come, and I think that if you embrace it with eagerness like that, you'll find the same value. I hope that's the case. Okay, so I want to just show one more thing, and that is, I just got to look around on my, oh, did I have that here maybe? No, I had it somewhere else. I'll find it. Oh yeah, here it is, yeah. Okay. Wish I could make this bigger. A little too small, but maybe you can still see it. So what we're showing here, this is a series of maps that are made from the Global Forecast System data by Alicia Bentley, who now works somewhere in the NOAA universe. She was a graduate student at SUNY Albany. Almost came here, but just couldn't finalize the deal. She wanted to stay home, and if she had come here, we would have done all kinds of great things. But she did them anyway at Albany, as Chelsea knows. So this is in black lines, sea level pressure. And then in the contours, not the contours, the colors shaded 250 millibar wind speed. So somewhere between 300 and 200, which we were talking about in our analysis first. So this is about the tropopause level jet in the Pacific. And then the red dashed lines and blue dashed lines are thicknesses between 1,000 and 500 millibars. They look like they're effectively column average temperature lines. And the transition is made to blue at 540 because there's a 50-50 chance in the wintertime when you have a 540 thickness over you that the precipitation that might fall on you is snow, not rain. Okay, so that's why this is kind of persistent. Now, Alicia, I'm showing you a really old map. This is an analysis from 6 Greenwich time on the 31st of August. Okay, and you can see most of the sea level pressure disturbances look like they often do, not really wildly tight horizontal spacing between the black lines, which would indicate a really intense small-scale cyclone. But here's a counterexample, well south of Japan, off of Taiwan. That's a tropical storm. And it's at the right latitude. It's at about 22 degrees or so. So that's a tropical storm. I don't know which one. Now, I'm going to show you a series of these maps as we go forward. And you'll want to watch, I want you to see how the migration, these are every 6 hours, I believe, how the migration poleward, now it's off the coast of China at that time, tropical storm number 1, how the migration poleward of these tropical storms tends to make these waves in the middle troposphere, particularly pay attention to the colored shading here, makes these waves amplify, they get bigger. And the reason is because the tropical storm is taking air that's from the boundary layer in the tropics, really warm, very little spin because it's down near the equator and it doesn't even have Earth's vorticity, gets thrust up to the high upper troposphere, and it finds itself creating a big bubble of low potential vorticity or low circulation air. And the consequence of that is it builds ridges. So the outflow from these tropical storms build ridges. And watch what happens. And look at, here comes another tropical cyclone. Now we're on all the way to 0Z on Thursday. Here's the next one. And you can start to see these waves developing in the downstream response. This one here that's crossing southern Japan is just about to hit a mid-latitude jet and a baroclinic zone. And that sometimes is a really potent interaction. Watch this. Look at how much faster they're getting pinker and redder, how much faster these wind speeds seem to get almost out of nowhere. I'll back up again. So there's a jet off the coast of China that's mostly blue, which corresponds to 50 to 60 meter per second winds. Well, look at that, pink, red, and curved. So there's a big change in a short amount of time to that jet off the coast of China. And watch what happens downstream of that jet now. And that means to the east, because the flow is going west to east. This whole structure is going to become very wavy. This is a region of high pressure, and there's going to be cyclones that develop upstream. Watch this. So this tropical cyclone number 1, look at how it's completely changed the orientation of that jet. Just a few times before, that jet was curved, but mostly east-west aligned with a little curve in it. Now it's been completely flipped to northwest to southeast. And the consequence is, here comes cyclone number 1 in the mid-latitudes. It's not a rebirth of the tropical cyclone, because that's still there. But the tropical cyclone outflow has changed the flow so dramatically in the far western Pacific that now we're going to start to have strong flow from the northwest, looking quite like what we had over us just to our north the other day. So watch that cyclone. That's cyclone number 1. And the flow has become very, very wavy in the central Pacific. Here comes tropical cyclone number 2, which I think reinforces that ridginess in the western part of the Pacific. And look at what it's done. This storm number 1 over the Gulf of Mexico, the Gulf of Alaska, is really intense. And there's going to be yet another such development as we move forward into the forecast. I think we're actually into the forecast mode now. I should have paid attention to that. Yeah, we're almost a week ahead. So there's going to be a lot of activity here in the Gulf of Alaska. There's going to be ridging over the western United States. And it's going to be pretty chilly air settling in at low elevations in the Intermountain West. In fact, there's a threat for Tuesday, which I think is just about a week from, it's almost valid at this time. There's a threat for snow in Boulder, Colorado in early September. And some people are theorizing, it's not a new idea, that the interaction of these 2 tropical cyclones with the broad waviness in the flow, the broad jet over the Pacific, has really amplified these waves. Look at how much north-south extent they have and how much east-west extent they have compared to what it looked like early on. I'll go back to the initial time. Look at that. There's almost nothing to it, right? It's just straight across the Pacific Basin all the way to the west coast. When you get to here, wow, look at that. Look at that jet going all the way to northern Alaska. And then we get to that point, we have a really wavy flow. So the interaction of tropical cyclones coming out of the tropics at this time of year. In the western Pacific, it's kind of not quite the peak season, but it's not that far away from it for tropical cyclones. And the jet is starting to rev up at mid-latitudes in the northern hemisphere. The interaction between these 2 is never more intense than it is right now. And sometimes that interaction can lead to substantial changes downstream in the flow and also substantial forecast trouble. Because if you don't get the tropical cyclone right, you don't get all this increase in waviness right, you get everything wrong in the whole northern hemisphere for a forecast period of about a week. And so everything can get screwed up. So it's really, really interesting. And in fact, it borders on this seasonal to subseasonal forecast problem. In October and late September and early October, my guess is that forecasts are generally the most terrible of the whole year over western North America particularly, and probably much of the Pacific Basin in the northern hemisphere because of this interaction. So we have an example of that right now. So are there any comments or questions about that? Pretty good, first week of weather for us. Sometimes you start the semester and it takes 3 or 4 weeks, Pete knows this, before anything interesting happens. And we got too much to talk about today. So, Greg.
I was going to mention that storm in Boulder. You can see it on there, where it's right on the edge of that.
I'll slide to another domain. Let's see if that'll help. North Pacific. Let's go to North America. Should be the same time. Yeah, this is the same time.
Yeah. This must be a little late. Is this Tuesday?
Yeah, this is, what's Tuesday? This is This is 060 Wednesday.
Wednesday,
So
yes,
let me
you gotta
back
go
up a
back
little bit.
24 hours.
Okay.
Because it's already gone, there it is right there.
Okay.
Hitting through. So you can see that pressure gradient up against the Rockies, and
Yeah.
if you had more resolution on it, there's a Kelvin wave effect going down. But this is not just a regular snowstorm. The ECMWF, European Center model, the GFS agree pretty well on this. It looks like there could be as much as 1 to 2 feet of snow.
That's
This is not
unbelievable.
over the entire Front Range,
Wow.
including Denver,
Yeah.
all the way out toward Kansas. So this is an epic snowstorm. Now, I think the earliest I can remember they ever had in Denver was the 4th of September.
Mm-hmm.
So this isn't the earliest, but it's pretty close. And having lived out there a long time, September snowstorms were a once in every 4 or 5 year
Yeah.
thing. But this is not normal.
Yeah.
This is not a normal September snowstorm. If they, and I think this is a good one for natural hazards class, because if they get a snowstorm at this time of year, that kind of a snowstorm,
Yeah.
that's going to cause $100 million damage.
Yeah, because it's a time wrong. Yeah, right, right.
And the reason it's going to cause damage, first of all, freeze, and the crops are just being harvested.
Right.
That's going to be a huge loss. But in the cities where you have all these trees, they haven't lost the leaves. They haven't even started to lose their leaves.
Yeah.
This is going to bring down big trees,
Yeah.
big 100-year-old trees. It's going to bring them down, and they're going to fall on houses
Yeah.
and cars. The damage is just going to be unbelievable if this actually happens at this time of year.
Yeah.
They can't. No place can handle that in this. This is a summertime snowstorm.
Yeah, that's right. I mean, the first 2 weeks of September are easily summer in almost every part of our country, including parts of Alaska. So, yeah, it's very true. And what Greg's pointing out is this is where the column average isotherms that are here in blue indicate quite cold air. This is here's Colorado. There's a strong contrast of temperature there, and this big anticyclone, for reasons you'll learn later on, will move straight south along that eastern side of this mountain range that's right about like this. Colder air filters in at low levels. It's bad news
Well,
for this kind of thing.
I think-
And there's upslope flow on top of that.
The thing to be aware is, the cold air is extending out toward the east from Denver. It's cold, but if this air just came through California would get down into the 50s, maybe something like that, or maybe even 60s. But Colorado's different because Colorado is at 5,000 feet above sea level.
Yeah, right.
And unless you pull air from sea level to 5,000 feet, you don't notice that elevation.
Yeah.
Today in Boulder and Denver, they're probably in the 90s. And when this comes through, they'll be in the 20s all of a sudden.
Yeah.
And that's just because the direction of the wind changes and you drag that air upslope and it cools as it expands, going upslope. And but what's so crazy about this time of the year and having a snowstorm is that moisture that's typical of summertime, the humidity from summertime is still in the air.
Yeah, that's
So
right.
the air that you drag up to Boulder, Colorado, or Denver, the air that you drag up there from sea level is coming up there with 60-degree dew points.
Yeah, that's right.
And if you drag enough of it up there, it's going to put down unbelievable amounts of snow. The ECMWF and the GFS are showing peak amounts over 2 feet.
Boy, unbelievable.
I mean, they haven't got that for a couple of years,
Yeah,
even
right.
in the winter.
Yeah.
But this time of year, you can get a lot of snow if it happens to be snow because of the humidities. So
Yeah.
it's going to be an interesting event, a very damaging event.
Yeah, and Elizabeth, we'll get to talk about this on Tuesday if we get our computer system working in that class, because this will be the thing we'll probably focus on, one of them. Yeah, it's going to be quite an interesting couple of days. And as you point out, I think even in addition to the heavy snow that's possible, just the transition from temperatures in the 90s, bone dry temperatures in the 90s, as is often the case there when it gets warm, to this kind of winter, landscape in a couple of days is enough to make people rethink who they're going to vote for, probably, or something. I don't know. I mean, it's going to be wild. So,
But it's not unprecedented. Like I said, they've had September snowstorms. I've seen them before too.
Yeah.
But This one's pretty strong.
Yeah, it's gonna be interesting.
Snowfall values? I haven't looked at it, but like, have you looked at the ensembles? Like, is a lot of the different ensembles showing, like similar amounts of snowfall?
I think we can get to that from the AOS page if you want, John. From the Weather Watch page?
Let's see.
I think I've got those spread
Yeah, I'm
on
just
some
curious
things.
what the spread might look like.
So where do I go there, Pete?
Go to our homepage is quickest. Weather, go to the Weather Watch links right at the bottom.
Oh, yeah, okay.
And then there should be GFS Ensemble, I forget what they call them. GFS Plumes, there you go. Oh, well, click on the link. Click on the link in the box.
Okay.
I've got a bad link there. And you should be able to click on, like, Denver, or zoom in.
Is this Denver? Is about where Denver is, right?
You can hit the plus sign and then drag the map around if you want. If you zoom in, you'll get closer. So there's the range.
That's quite low.
So you're looking at QPF there. If you go down to the variable right below the map.
Let me just, I got my wrong glasses on.
Yep.
I'm just gonna find Denver first.
Yep.
That's it, okay. Come on, what's the matter? Okay.
And then right there, you can change that to probably precip or snow. What is it?
Is there snow? Is that snow?
Yep.
Pretty wide range.
Anywhere between 2 and 14 inches.
Yeah, depending on how the ratio, you know, the ratio of liquid, and that's at Denver.
Yeah,
You
right.
have Boulder that's up against the hills there. I mean, if you can get one there, it's probably not enough.
This is, let's see what that's like. That's not quite Boulder, but
Yeah.
I don't know what that is. It looks like Greeley or something.
yeah, well, it's gonna snow there on Tuesday, it looks like. It looks like almost no solution doesn't see that, but some of them see biblical snowfall amounts and some of them see nuisance snowfall amounts. But I think anything that comes on September 9th, wherever you are in the United States, is more than a nuisance. It makes you nervous about the coming season.
Almost
But it's-
any of those events is going to cause a lot of damage.
Yeah, that's right. I mean, I last time I traveled for work, it was early March, and it was West Boulder, where the hills get up a little higher and there's more trees. People were complaining. It had 2 inches of snow the night before, and branches were coming down because it had been warm, and they started to leaf out, carried a lot of snow. And it's even worse now, of course. So,
Yeah.
any other comments or questions? Well, Pete, thanks a lot for coming over and getting this thing set up. It looks like this will work pretty well, and we have room for spillover. We can go all the way back to the rooms, and nobody has to use any of these desks during this time. So, for those who are listening and maybe want to come into town or something, or just students who want to come in, there's going to be time and space to do that. So, I'm a tech phobe in some ways, as Pete knows. And I was able to get this console working by myself in 2 seconds. So it's very intuitive and works well. None like what we've experienced yesterday. So looks like a good setup. Okay, well, thanks everybody. Thanks, Greg, for a good conversation, and we'll see you all next Friday, same time.